Okay, so let's be so today I will try to conclude our discussion on kernel methods, and then we will start looking at a new type of learning algorithms which are called support vector machines. And the reason we are discussing them after kernel methods is because support vector machines are one of the classic sort of examples of kernel methods, but in their vanilla form they are not they don't use any kernel. They are more of linear models. So I could have discussed it before, but after doing the kernel discussion, it makes more sense. All right, so today we are going to talk about kernels. So if you remember, last time we did discuss the notion of a kernel, right? The main point there was that by using a kernel function k, which essentially computes similarity between two objects, you can generalize linear models to be applied to non-vector data, right? So the main thing you want to remember is here, right? So if you do typical regression, the way you do typical regression is that you have this equation, right? So you want to predict the value y star for a new input x star, right? And actually, let me go back a little bit. So this is the equation that we have seen, right? So this is ridge regression. So you estimate the parameters using your training data, and then to compute the prediction at a new point, you do y star is equal to w transpose x star. And actually, this would work even if you have if you're doing logistic regression, because in logistic regression, all you do is you compute w transpose x star and then you do the sigmoid of that, right? So the kernel methods would still hold. Here I'm just giving you an example for excuse me, for linear regression, right? So the main idea is that this is how the expression looks like, but then we rearrange it using this Sherman-Morrison-Woodbury formula. It looks like this, and then it turns out that if you analyze these parts, these are the parts where you have the input data. It turns out that the input data always exists as a dot product between a pair of objects, right? So either you're taking a dot product between two training data objects, or you're taking a dot product between your training data objects and your new object. So then it turns out that instead of using the explicit vector representation and then doing a dot product, you can come up with a function k which can compute the dot product, and which means that you can then construct this matrix and a vector k, this part, and you can express your y star or the prediction like this, right? So the next thing that comes out of this is that we don't only, this means that we can use some other arbitrary function as well, not just the dot product, right? So we call those kernel functions, and the matrix that is created by that is called a gram matrix or a kernel matrix, right? And then we talked about what are the different kernels that you can have, right? The simplest kernel is, of course, the dot product itself, but that there you are still assuming that your data is in a vector space, but you can come up with other kernel functions that can be applied to non-vector data. So maybe your objects are two images or two strings or two graphs, right? So you can come up with kernel functions and use them, but there are some rules about the kernel function. Just have any arbitrary kernel function. There are only some kernel functions that are allowed. In particular, the kernel. So symmetric means that, ixj same as kxjxi, of course. The gram matrix, that k matrix, should be positive semi-definite. Why do we do that? Because at the end of it, you that matrix, right? So if it's not well formed, you will, if it's singular, you won't be able to invert it, right? So we put a constraint like that, all right? And then I also talked about, okay, so then comes the question, how do we design new kernels? So you can come up with any kernel function, but then you have to prove that these are true, right? These two especially. However, there are some rules that you can use. So there are some kernel functions that people have already come up with, and they have already gone through the trouble of proving that they are valid kernels. And then there are You build fancier kernels by using these individual kernel functions, right? So for example, you can have a kernel which is just a constant times this kernel, or it could be some functional form of applying some other function, and there needs to be some constraints on this function that I still don't know, but I'll come back to that. You can do a version of kernel exponential. You can add two kernel functions. You can multiply them, subtract them, divide them, not divide, subtract them, and they would still be valid kernel functions. All right. So that is the idea. But now today we're going to look at some particular kernels, right? So there are one class of kernels, family of kernel functions. They're called Mercer kernels, which are kernels which are positive definite. All right. So last time I was talking about what is a positive semi-definite matrix, right? And what is a positive definite matrix, right? And there are certain rules that they need to follow. And you can, an analogy in the number space is that a positive semi-definite matrix is like a non-negative number, and a positive definite matrix is a positive number, right? So if there is one particular type of kernel that you will see a lot, which is called a Gaussian kernel or a radial basis function. So let's look at that one a little. I'm inputs objects xi and xj, and the value is essentially ext 1 by 2 sigma. So sigma is like a hyperparameter of this kernel function. All right. So this is something that you provide. You don't learn this. So if you look at this, right, much like the exponential part of a normal distribution, right? Gaussian kernel. What it essentially does is it computes the similarity between two objects. So if now this is essentially a Euclidean distance, right? So with what norm vector in d-dimensional space, Sj is also a vector, Xj is a vector, right? Two bars essentially means the second two norm, L2 norm, which means you are squaring the values and adding them up. And then square means that you're just taking the square sum. If I don't have this square here, that means you take an under root of that. So that is like an Euclidean distance, but here it's the square distance. And then applying. If you look at this more carefully, essentially what this does is that if two objects are very close, then this value will be very high, right? It will be close to 1. Because if these two objects are exactly the same, this part will be 0. P of 0 will be 1, right? If these are far away, then this value will start tending towards 0, right? So it's that kind of a kernel. So it kind of is and the way it drops out is kind of like a Gaussian curve. So in fact, in the notebook, I had an example. So this is how it looks. So here the example is for when your d is 1. So let's say data is only in one space, right? Look at this. All right. So the value of this kernel function will be high, will be close to 1 if other object is very close to it. And as you go far away, it kind of dies out, right? And the width of this bell is governed by that sigma parameter. So that sigma parameter tells you how fast you want to sort of die out, right? So if your sigma is very loose or very broad field, right? So and then if it is high, then you make it very narrow. And then we'll see the use of this. We will see it in many ways. Of course, we have also looked at the cosine similarity earlier as well. Any questions so far? Right. So last time I did talk about. Was there a question? Okay. Last time I mentioned that the effect of a kernel function is essentially when you apply a kernel function, what you're inherently doing is you are projecting your data into a new space, right? So if you remember our calculations last time, here we went the other way. We said, how about we apply some feature, new features by applying these polynomial or any basis functions to your data. And then what it turns out is that in this new space, when you do the dot product, you can replace it by the kernel function. That was our whole story. Any valid kernel, radial basis function, any Mercer kernel, it in some way amounts to projecting your data into a new space. All right. So for example, means that you're projecting your data into some space and then you're doing your linear regression in that space, right? With radial basis function, it so happens that the F function is that you're projecting your data into an infinite dimensional space. Okay, so which sounds strange, but I'll show you why it is so. But that is the idea. So you can think of it that that really helps, right? So the idea is that you're trying to fit a line to points, right? But in the original space, maybe the points are all over the place, so it's not easy to fit a line. But when you go to an infinite dimensional space, it might be easier to fit a line, right? So I did give you some examples earlier. So for example, here, right? So there's this example in the notebook that we did last time. So let's say this is our data. This is in one-dimensional space, right? So there are two types of points, triangles and squares. Now the data is in one-dimensional space, but this data is not linearly separable. Like it's not easy to draw a line which distinguishes between these two types of points, right? However, if I map it into this two-dimensional space, where one dimension is still x and the other one is x squared, then the new data, the data in this new space, is linearly separable. You can draw a line in this 2D space. And I showed you last time that then when you bring this line back into the 1D space, it looks like a curve, right? So let me quickly show that, right? Here it was. This is your data. You project it to the new space easily. And then when you bring the line back, it looks like, right? So that is the idea behind kernel methods. So you project data into new space by applying these kernel functions, learn a line there, bring it back, and hopefully it will be linearly separable. Or hopefully it will be separable, right? And you can do that in other cases as well. For example, let's say your data has two dimensions now, or two attributes, x1 and x2. And let's say these are the two types of points. Now, of course, you cannot draw a line that distinguishes these red and blue points, right? However, if you map it into a 3D space, so from 2D, if you go to a 3D space, by applying these transformations, so instead of x, which was just x1 and x2, you replace it by x1 squared under root 2 x1 x2 and x2 squared, then this is how it will look like in that 3D space. In this 3D space, you can draw a plane that distinguishes between these 2 points. When you bring this plane, it will look like a circle, right? If you remember, I showed it to you using paper as well. So if you had data in that form, you project it into 3D space, you can draw a plane. When you look at it back in 2D space, looks like a circle. So that is sort of the advantage of a kernel function. All right. Okay, so then there is this square dot product kernel that I just talked about, right? So that is the one that lets you draw a circle, right? Now, so as I said, right, every kernel kind of amounts to mapping data into a new space, right? For some kernels, for example, a kernel like this, you can explicitly say what is the new space, right? So the kernel function here was the square dot product, and the feature transformation is this. So you can get that mapping, but in some cases it might not be easy. So let's look at this kernel. This is our radial basis. Earlier, this is like this transforms the data into an infinite dimensional space, takes it there and then comes back, right? If you're Indian, it is like the Rajnikant of machine learning, and otherwise like Chuck Norris of this. It goes to infinite, comes back. Right? So now let us see how it does that. So the way to look at it is, let's assume that sigma is 1 for now, right? So of course, this is the kernel function, right? But let's say sigma is 1. Then if you look at kxj, you can express it in a very way. So understanding RBF kernel, right? So let us assume, so of course RBF kernel can be written as this: k of two objects xi, xj is exp minus 1 over 2 sigma square xi minus xj, the square root of the L2 norm, right? However, let us assume that sigma is equal to 1 and d is also 1, which means that your implies that xi and xj both are in one-dimensional space, right? Just for simplicity. So which means that k of xi comma xj can be written as exp minus 1 over 2, right? Because there's no sigma square, xi minus xj square, right? In fact, let's assume that 2 sigma square is 1. So we just get rid of the whole thing, right? So then we can open it and say that this is same as exp minus xi square minus xj square plus 2xi xj, right? And you can write this as exp minus xi square times exp minus xj square times exp 2xi xj, right? So now what we are going to do is we're going to do a small trick. Now if you remember your math, exp of any function, right? So exp of any a can also be written as a summation, right? It can be written as summation k equal to 0 through infinity 2 power k ak divided by k factorial. So that is just a mathematical result that is, that is known. I think it's called the Maclaurin series expansion, right? Yes. Yeah, k factorial. Yeah. Yeah. I mean, this part is not very related to the course in general, so don't worry about the exact expressions. But the idea is this. So, which means that I can replace this by exp minus xi square, exp minus xj square, summation k equal to 0 through infinity 2 power k, and then instead of a, this is xi xj, right? So xik xjk divided by k factorial, right? So, or you can write it as exp minus xi square, and you can bring these inside because these are not dependent on k at all. So summation k equal to 0 to infinity exp minus xi square times root 2k xik divided by root k factorial, and exp minus xj square, where this come from, root 2k xjk root k factorial. Yes. Yeah. Here? I mean, I just replace a with xi xj. Oh, right, you're right. So there's a 2, that's why I have a 2k as well. So I replaced that a, oh, I think this is not there, right? It's just this, sorry. Yeah, good catch, yeah. So this is the Maclaurin series expansion, so that's why I wrote it like this. So at the end of it, you can sort of, so I broke this part into two parts so that I can have half of it with this, half of it with that. So at the end of it, what starts happening is you can think of this as a long vector, I mean, with k, and this as a long vector, right? So think of this as a vector in which it goes from k equal to 0 through infinity. So it is going to be exp minus xi square times under root 2 power 0, xi raised to 0, whatever 0 factorial, and then 1, 2, 3, all the way there. And then you can think of this also as a vector, right? And this thing is nothing but a inner product between these two vectors, right? That's a dot product between this vector and this vector. Now, because k goes from 0 through infinity, it means that this is going through, this is an infinite dimensional vector. So what it ends up happening is, what you're doing is you're replacing your xi by these infinite versions of xi. So you're applying these functions. So think of these as infinite basis functions that you apply to xi to map it into this infinite dimensional space, and then you're taking a dot product in that space, right? So that is why we say, now this math, I probably hurried through it a lot, but the idea behind this is that by this math you can see that applying this kernel function essentially means mapping each one of these data objects into this infinite dimensional space and then doing a dot product. So that is sort of the power of radial basis function. All right, any questions so far? Yes.
Well, you're talking about bringing back the line in higher dimensions.
Right.
So for the one-dimensional example, I was expecting two points. I thought you would be projecting it.
Right.
Like so if you got a curve, like in the other dimension, the three-dimensional example, you have a point.
Yeah.
And then the image of that would bring it back into the circle,
Right.
right?
Yes. Yeah.
So the one-dimensional would it not be the line intersecting the parabola?
Yes, so you are right, but the problem is that it's not a problem. But essentially, what happens here? Well, actually, I should go here. Right? So the question here is that this is the line that you learned in this 2D space, and then when you try to bring it back in the 1D space, because these things are not defined. This is a one-dimensional. Oh, you sorry, it was just for me. Right, so here it is. So the question is that in this example, right, we mapped our data from 1 to 2-dimensional, right, and then we drew this line in the 2 dimensions. Then I say that we bring it back, right? When we bring it back, actually, because this is a one-dimensional data, so this part doesn't make sense. There's only one dimension in space. So actually, it should just be these 2 points. You're right. And the idea is that these 2 points help you distinguish between the 2 points. But I'm just drawing the 2 dimensional. But yes, that's a good point. But in 3 dimensional, it's easy to see that it comes back as a circle.
What I guess then what map are you using to get the problem? Like bringing that whole line back?
Oh, I mean here, right? So all I'm doing is that I have the equation of this line, right? And then in the 1D space, I'm applying the function to each point here. So from here till here. So when you apply that function, it's a quadratic function. That's why you get those 2 points. But you are right. I mean, to be correct, when you bring this line into this 2D space, all you should get are these 2 points where it intersects, because there's nothing here in this one. Yeah. Right. Right, good question. So we did talk about mapping the data, right? After that, this line, so far I'm just using linear regression, because because we started with that discussion, right? We assumed that, where is that? Right here, right? We are assuming that we are going to use a linear regression formulation to learn the line in new space. But we can do much more. So we are going to discuss that later on as well. But so far, I've been just using linear regression, logistic regression to do this. But later on, we'll see how to expand it. Any other questions? Yes. Oh, that was just here, this square root. I just basically I had this part, right? So I wrote it as square root of this times square root of this, so that I have two parts which I share one with this and with this. This is just to get this form. But all right, any other questions? All right, so let's move on. So now we are going to see. So as Dana said, we can use the kernels to project into new space and then use our old linear regression, logistic regression to learn our boundaries. But you can do other things as well. And we are going to see something called kernel machine, which is another type of classifier. Okay. So kernel machines are very simple. What they do is they use these kernel functions to generate new features. Okay. So what they do is they take your data, right? From the data, they select some representative points. We call them these centroids, okay, mu1 through mu k. So these are essentially, you have this training data out of which you could either select k centroids or you can select some k points from that space any way you want, right? And then you compute this kernel function. So for every data object, what you do is you compute this kernel function with each one of these centroids. Okay, so now your data becomes this. So x could have been anything. X could have been a d-dimensional vector, or x could have been some arbitrary object, could have been images or documents or something, right? But what you do by applying this function, you're mapping it into this k-dimensional space and then doing your linear regression there or logistic regression there, whatever you want, right? So that is another form of a classifier. Okay, so it's not a true classifier in the sense that it's not a new mechanism to learn or anything. All it is your data into a new space and then using some old classifier or a regression method to learn the boundaries or whatever, right? However, if you use the Gaussian kernel that we saw earlier, then those classifiers are also called RBF networks or radial basis function networks. So if you think about this, right, and between radial basis function network and a neural network. But the only difference is that it only has one hidden layer. So what you're doing is, because think of this Gaussian kernel, right? This Gaussian kernel looks very much like a sigmoid function. So it looks very much like a neural network. But the idea is very simple. You have a data object. You convert it into k-dimensional space by applying these radial basis function kernels using some k centroids, and I haven't told you how to get those k centroids, but then when you get this new space, you can learn your boundaries. All right. Now the question becomes, how do you choose these centroids? And you can do them in many ways. You can randomly select some points from a data set, and we haven't talked about clustering so far, so that's why I don't want to go into this right now. But there is some technique that lets you get some representative centroids, and you can use them to in your radial basis function network. So I want to look at this here. So here, so again, we have seen this example before, right? So this is your data set. But what I do here, but since I generated this data, right? So if you look at this, I generate the data. So the way I choose 4 means, and then I sample from a multivariate normal distribution with some sigma, some standard sigma, and I get these samples. All right. So that means I know these 4 means. I use those as my centroid. Okay. So I'm cheating a little bit. But then what I do is I apply the radial basis function. What I do is I take my data and I with one of these, right? So this is the part that happens here, right? This part. And now I have a new data set in which my, so this is my kx, right? And then I learn logistic regression in this new space, kx and y. And then I plot the boundary. So this is what it looks like. It learns these perfect circles around the the response. All right. So that is sort of the power of RBF networks. Its ability to learn these non-linear surfaces. If you remember, right, in logistic regression, we tried to do this non-linear mapping earlier as well, where we applied some basis functions, some polynomial basis functions, but polynomial basis functions were not able to learn very nice boundaries. They were learning polynomial boundaries because that's what they are supposed to do. But with radial basis functions, you learn these, what should I call them, globular or circular boundaries. Fantastic. So this is just a very discussion because I mean, of course, radial basis functions are very interesting and they work very well in practice, right? Yeah. Okay. So, I mean, implementing an RBF is very easy. So let's say you have your training data. Let's say your task is to distinguish between two types of documents. All right. So let's say you have a bunch of training data. So RBF network. So let's say you have your training data is essentially a bunch of documents. So this is a document, and so on. And you have labels for them. So this is your Y, this is your X. Y is +1, +1, -1, -1, +1, and so on, right? And you want to learn some classifier such that you get a new document, X star, and you want to predict what Y star is, right? So what happens in RBF network is that you will choose some sample documents somehow, right? And treat them as your centroids. So let's say here you're choosing 3 documents, and I'm going to call them as my 3 centroids. Now, how do you choose them? You can either randomly choose them, right? Or you can do some sort of clustering here and choose the representative ones, or you might use some domain knowledge to choose these 3. Say, okay, these 3 are the typical documents that are there. Then what you do is you take each one of your data objects and you compute its RBF value, with each one of these, right? Of course, here we assume that you are able to represent them in the d-dimensional space because RBF requires that. So then you will get 3 values, k1. So let's call this x1, x2, x3, x4, and so on. So this one will be k11, which means the kernel value between 1 and 1, k12, k13. And same way you compute the kernel function with each one of them, right? So now for each object, suddenly you have 3-dimensional features, k11, k12, k13. For the second one, you will have k12, so k21, k22, k23, and so on, right? And you can maintain the labels here. So now this is your new data. And then you can do your logistic regression to learn the boundary, all right? Any other questions? All right. So now I quickly want to move on to the next topic, which is one of my favorites. So that's why I want to start with it today, which are the notion of maximum margin methods. And in that, we will learn about support vector machines. Right? All right. So let's get a sense of what it is. Of course, we don't have enough time today, so we'll look at them later as well. So this is the form of a classifier that we have seen so far, right? The only difference here is here we are using a different weight for the bias term. In logistic regression, linear regression, what I did was we said let's include the bias in X itself, right? Add a 1 in the end, and then assume that W will have one extra term. But for these classifiers, just because it's easier to explain it that way, we are going to assume that we do not explicitly add the bias term, but we have a bias term here. So in our previous discussion, B would be same as your W naught, which would go with the intercept, right? But this is the form of classifier that we have seen so far, right? We use this value to get your Y, right? So now let us look at a geometric interpretation of this. right? So the idea behind behind these linear models is that they try to learn a line, right? They try to learn a line which can distinguish between two classes of points, right? And here we are assuming that our points are linearly separable. So if you remember from third week, we talked about perceptrons, right? So we learned about two types of perceptron. The first perceptron learning algorithm assumed that your data is linearly separable, right? And there was an algorithm which helped you learn this line, right? And the idea was that if the data is indeed linearly separable, then perceptron training, the method that we looked at, it guarantees that it will learn the right line, right? It will learn this line. However, this is not the only line that separates these two types of points, right? I could have drawn a line like this, or a line like this, or a line like this. All of them would have separated the two types of points. So the question is, which line would perceptron learn? And the answer to that is that it will learn whichever line it finds first, right? If you remember the perceptron learning algorithm, it starts with some initial estimate of your W, and then it adjusts it, right? So depending on what your initial estimate was, wherever it reaches the line which distinguishes your data, it stops there. After that, because it won't make any more mistakes, it won't change that, right? So if you, let's say, start your line like this in perceptron, and slowly as points come in, it keeps on adjusting. Once it reaches here, it won't change, right? Because if you learn your perceptron algorithm, if you remember your perceptron learning algorithm, the only time it changes is when it makes a mistake. But once it reaches here, it won't make any more mistake. But this is a perfect line, right? However, it turns out that this might not be the best boundary, right? So the question becomes, which is the best boundary? Is this the best boundary? Is this the best boundary? Or, so that's the question. What is the best boundary, right? So that is where we introduce this notion of maximum margin, all right? So the point here is that if you have two types of points and you can draw many lines through them, the best line that would give you the best generalization error, because that's the one that you want to minimize, right, is the line that goes exactly between the two types of points, right? The one that maximizes the margin. And in next class, we will actually quantify what margin really means. But today, I just want you to sort of go back with this notion of general margin. So if you have two, so the principle of maximum margin. If you have a data set in which you have two types of points, all pluses and all minuses, right? And they are linearly separable, then if there is enough space, you can draw infinite lines that give you zero training error, right? They're all going to separate your line. But the best line is the one that goes right through the middle, okay? The best line. Now, what do you mean by best line? Which means the line that will guarantee the best generalization error or the lowest generalization error, right? So the lowest generalization error will be given by the line that goes, and this is more colloquial, right between the points. But in technical terms, it is the line that maximizes the margin, okay? So think of these 2 points, right? So you want to draw a line such that it is far away from both types of points, okay? So that's called the maximizing the margin principle. And in the next class, we will look at one algorithm, which is called support vector machines, which is designed to maximize this margin. And because it is maximizing this margin, it means that it guarantees best generalization error. So that is the strong point of support vector machines. So in next class, what we will do is we will see how to mathematically quantify the margin and then come up with an algorithm that maximizes it, right? So you get the sense, right? So there's an objective function that we will define, which will try to maximize this margin, and then we'll come up with an algorithm which is just an optimization algorithm that will help you sort of ensure that you get that. Any questions so far?